After this video, I want you to be able to list the total number of electrons needed to fully occupy each main energy level. And I want you to be able to state the Aufbau principle, the Pauli exclusion principle, and Hund's rule. Getting started with electron configurations. The quantum model of the atom improves on the Bohr model because it describes the arrangement of electrons in atoms other than hydrogen. Remember that the Bohr model of the atom only described hydrogen or monoelectric atoms. The arrangement of electrons, plural, is known as an atom's electron configuration. Because atoms of different elements have different numbers of electrons, a distinct electron configuration exists for each atom, for the atoms of each element. Like all systems in nature, electrons in atoms tend to arrangements that have the lowest possible energies. The lowest energy arrangement of the electrons in each element is called the element's ground state electron configuration. A few simple rules, combined with the quantum numbers and the relationships discussed last section, allow us to determine these ground state electron configurations. So, rules governing electron configurations. To build up electron configurations for the ground state of any particular atom, first, the energy levels of the orbitals are determined. The electrons are added to the orbitals one by one according to three basic rules, but remember that real atoms are not built up by adding protons and electrons one at a time. The first rule shows the order in which electrons occupy orbitals. According to the Aufbau principle, an electron occupies the lowest energy orbital that can receive it. Figure 4-16, which is on page 105 of your textbook, shows the atomic orbitals in order of increasing energy. The orbital with the lowest energy is the 1s orbital. In a ground state hydrogen atom, the electron is in this orbital. The 2s orbital is the next highest energy, and then the 2p orbitals. Beginning with the third main energy level, which means n is equal to 3, the energies of the sublevels in different main energy levels begin to overlap. Note that in this figure, for example, that the 4s sublevel is lower in energy than the 3d sublevel. Therefore, the 4s orbital is filled before any electrons enter the 3d orbitals, which means less energy is required for two electrons to pair up in the 4s orbital than for a single electron to occupy a 3d orbital. So, question. Once the 3d orbitals are fully occupied, which sublevel is occupied next, according to this figure? The 4p orbitals will begin to fill after the 3d orbitals are fully occupied. The second rule reflects the importance of the spin quantum number. According to the Pauli exclusion principle, no two electrons in the same atom can have the same set of 4 quantum numbers. The principal, angular momentum, and magnetic quantum numbers specify the energy, shape, and orientation of an orbital. The two values of the spin quantum number allow two electrons of opposite spins to occupy the same orbital, as shown in figure 4-15 on page 106, which I have on this slide. Notice that in that 1s orbital, there are two electrons, each represented by an arrow, and they have opposite spins, represented by different orientations of the arrows. The third rule requires placing as many unpaired electrons as possible in separate orbitals in the same sublevel. In this way, electron-electron repulsion is minimized so that the electron arrangements have the lowest energy possible. According to Hund's rule, orbitals of equal energy, each occupied by one electron before any orbital is occupied by a second electron. And all electrons in singly occupied orbitals must have the same spin. Applying this rule shows, for example, that one electron will enter each of the 3 p orbitals in the main energy level before a second electron enters any of them. This is illustrated in figure 4-18 on page 106 of your textbook. You can see that in figure A, only 2 electrons are in this particular sublevel, and they are each in separate orbitals and all with the same spin. When we add the next electron, as we see in B, again, we see each orbital is singly filled, and each of those singly filled electrons have the same spin. And once we go to add the 4th electron to this sublevel, we go back and we fill one orbital doubly with 2 electrons, and we make sure that they have opposite spin. At this point, I hope that you can list the total number of electrons needed to fully occupy each main energy level, and you can state the Aufbau principle, the Pauli exclusion principle, and Hund's rule.